Okay, so for this AC series, reminder for series, if I wanted to label nodes, here's a node, here's a node, here's a node, here's a node. And one thing that I noticed on the exam was that some people were saying series was anything that had a node in between elements. And that is true that there is something in series if there's a node in between elements. But what I mean whenever I say exclusively share is that there's one wire coming in and one wire coming out. So this inductor VL, I'm sorry, this inductor right here of 70 millihenries and 50 microfarads, in this node, there's one wire coming into that node and one wire coming out. So they exclusively share it. Whereas on the exam, if something was like this, well, now the 50 microfarads would not be in series with the 70 millihenries. These two together, which we'll do tomorrow by putting them in a box, that will be in series with the 70 millihenries. But by itself, this 50 microfarads now, this is in series. So that's why whenever I say two nodes or two elements exclusively share one node between them. So there's a few people that seem to make that mistake on the exam, so I wanted to clear that one up. All right, so the first step that I said is anytime that I have an AC problem, which is AC, right? Anytime I have an AC, I'm gonna first check, do I have everything in ohms? Well, my R is always gonna be in ohms, but these are not in ohms, right here. This is C, capacitance. This is L, farads. So the first step that I need to do is I need to find the impedance of each of those. And you could start by just doing the reactance, but the impedance of an inductor is J, Z is a vector, J XL. Well, what is XL? Except if you go to the formula sheet, do I have it open? I don't have it open. But the JXL is omega L. So what it says on the equation sheet is that XL equals omega L. Notice that X, reactance, that will be in ohms. It does not have a J component. Whenever I put it with the J component, then it becomes an impedance of Z. Okay, so I have J, my omega right here is that. There's my omega T. So omega is 1,000, and my L is 70 millihenries. So the Z of my inductor is J 70 ohms. That works out that the 1,000 and the milli cancel out, so it does turn out to be 70 ohms. Now the Z of a capacitor is negative J 1 over omega C. On the equation sheet, it says X sub C is equal to 1 over omega C. That would also be 1 over 2 pi F. In this case, we have omega, not F, so we'll use the omega. And so I can plug in this, negative J 1 over 1,000. And then I have 50 microfarads. And that comes out to negative J 20 ohms. So if you wanted to write here, if you could, negative J 20, and right here, positive J 70. Just to remind yourself that those are the ohms that are getting plugged in. So now my Z total, I'm just going to add them up. The equation sheet for series element says Z1 plus Z2 plus Z3. So my first one was the inductor, positive J 70. You can write ohms, minus J 20 ohms plus 50 ohms. And if you plug it into your calculator, you can do this one in your head, but it will give it to you as, if you have it in rectangular form, if you have it in the rectangular form, it'll say 50 plus 50. On your calculator, it's like I, but we treat it as J because I is already current, and this is ohms. If you have it in polar, it'll say 70.7 angle 45 degrees ohms. And that's saying the same thing, because if I was to plot the Z total along here, it's right there. and it's an equilateral triangle of 50, positive 50. And so that vector is what, this is an impedance plot. So you can even tell right now that this overall circuit is inductive because the 50 J here is positive, right? So it's overall inductive, but its theta angle of 45, theta Z, is equal to 45 degrees. It's positive, therefore it's inductive. All right, so this is overall an inductive circuit. Now for I total, back to our favorite law, V equals IZ. But note that I have my E in a time domain. I need to put my E of, which is V here, into a vector. Right? And usually we'll put it into the RMS phasor, which is the vector. The RMS, we do that because if we're ever going to do power, we need the RMS value. So I do 170 divided by √2. Take the angle, and it was 0 degrees. That would also mean that it's the reference phasor, is a term that we'll use. See how the angle up here, I'll put it in red, right there in the top right. That's 0. That means this is the reference phasor. So now whenever I plug that in, it comes out to approximately 120, angle 0. So we'll rearrange this. I equals V over Z. And we're doing all the totals, V total, Z total. And so my V total, 120 angle 0, Z total. You can write either one. You can write it in rectangular, your calculator can handle it. Just make sure that you either do your parentheses correctly or you use the fraction button. And I total comes out to 1.70 angle negative 45 degrees. Now note, and I'll box these in red. There's Z total, here's I total. We will typically put our, I don't care whether you use rectangular or polar for Z, but for V and I, we put them back into polar so that we could put them back into the time domain. Makes sense? So now we found I total as a phasor. So C is determine all of these. Well, if I know the I total, and these are all in series, and series elements have the same current, well, the current coming out of my source is the same as the current flowing through the inductor, is the same as the current flowing through the capacitor, is the same as the current flowing through the resistor. They all have the same current flowing through. So if I needed to do each of these, I could do Ohm's law for each of them. You could also use voltage divider rule. That would be acceptable because these are all series elements, and voltage divider rule is for series elements. So the voltage of the inductor, the current going through the inductor, times the Z of the inductor. The current, 1.7 angle negative 45. The Z of the inductor is just J70. If you wanted to write 70 angle positive 90, that would also be correct. I just find writing J's faster than writing angle 90. So this comes out to 119 angle 45 degrees volts. V of the capacitor is the same one, the I going through the capacitor times the Z of the capacitor. The I of the capacitor is the same as the I total, 1.7 angle negative 45. And now we have negative J20. And that one is 33.9 angle negative 135 degrees. The voltage of the resistor, should have cleared this out because I'm drawing over, kind of getting a little bit messy. But it's the same, the current going through the resistor is the same as the the current going through the resistor is the same as the I total. The Z of the resistor will just be the ohms. So in this case, 1.7 angle negative 45. The Z of the resistor is just 50. Right? There's no imaginary component of a resistor. It's purely on the real axis. And that comes out to 84.8 angle negative 45 degrees volts. There's my 3 parts. And now part D says to confirm KVL. Verify KVL. KVL says what goes up must come down. That doesn't work quite as well because of the way that the rises and the falls work with the angles, but it's still that the sum of the voltages in a loop equals 0. So let's just put it that way. We'll just say the sum of the voltages in the loop. It's still a rise. We'll call it like the polarities matter. So if we're looking here on the graph or on the circuit, notice how the positive is still here and negative, and the positive is still here and here. So that's pretty much how we reference it, that they will still look like a drop. But if we just say the sum of the loop, so what this means is that all 3 of these, 120 volts, angle 0, that's what was providing as the source, and all 3 of those together now, 119 angle 45 plus 33.9 angle negative 135 plus 84.8 angle negative 45. And when I sum all of those together, I get 120 volts angle 0. So we verified KVL. Now what this is doing right here is it's just plotting all of these on the time domain. So notice how the voltage source is right here. Its peak goes up to the 170 and it crosses through 0. So that's kind of the 2 things. If you ever were to plot it